Welcome. My name is Xenia Flamm, and we're here today to interview François Labourie after our conference on 20 years of Anosov representations.
Hi, I'm Jeff Danciger. So let me start by saying a little bit about François. He did his PhD with Gromov in 1987, and then he started his career as a CNRS researcher, and then became a full professor in Orsay for a long time there. And now he's been in Nice since 2014.
Yeah.
He's had many prizes and accolades, just a few. He was an ICM invited speaker in 1998 in Berlin. He won the prize at the First European Congress of Mathematics in 1992, and 2 prizes of the French Academy of Sciences in 1993 and 2016. He's also held 2 ERC advanced grants, and he's done a lot of service to the community. For example, he's been a member of the Opel Prize Committee for both 2019 and 2020. So thank you for speaking with us, François.
Okay,
Yeah, thank you for being here. Maybe I can start
Okay.
and ask you, could you introduce your research like in a way that maybe non-experts might understand?
Okay, so I'm going to introduce actually our research. So we are all interested into discrete subgroups of Lie groups. And our first starting example is the interplay with geometry. And the first starting example is this picture, more or less. So it's a tiling of the hyperbolic plane. So I guess all of you know about these beautiful drawings by Escher. And you have repetition of this pattern, which is here a triangle by some, or triangle or hexagons, octagons by some movements. And these movements form a group, what we call a group. And the relation is to the interplay between the dynamics of the action of this group. So you see that if you follow a random path, you're going to end up with this boundary here. And the relation with geodesics, which are this shortest curve in the hyperbolic plane. And one of the starting results is to say that essentially a random walk on the groups is like a geodesic. So we see on this example that there is this interplay between geometry and dynamics. And this is something that we like a lot.
So I want to ask you about a paper you wrote 20 years ago. It was titled Anosov Flows, Surface Groups, and Curves in Projective Space. This is the paper where you introduced the notion of an Anosov representation. The conference this week here at the MPI has been focused on the study of these representations and the developments over the past 20 years since your original paper. So I was hoping you could take us back to the time when you were writing that paper. Like, what inspired you? What ideas from your previous research endeavors sort of came together to bring you to this idea, which has become quite influential today?
Yeah, so I'm going to give an history course about the landscape of the mathematics at the time. So maybe for me, it started 10 years before. And the first time I become interested into discrete subgroup of Lie groups was this paper with Benoit on Foulon about Anosov flows and smooth foliations.
Mm-hmm.
And we came up with a question of what sort of discrete groups appears in Lie groups so that there is this homogeneous quotient, gamma mod g mod h. So that was the topic of one of the lectures during this conference. So in other words, we had to understand what sort of discrete groups of Lie groups appear here. Mm-hmm. And so I was interested in that from that question, and it started with the question of finding this homogeneous quotient. So Foulon went to study more Anosov flows, and Benoit went to study actions of groups, and that's where he introduced his ideas of limit cones. So it started also from that paper. So that was my origin. And my other background was that of more analytical side, which is like a holomorphic differentials and surface with constant curvature, this kind of thing. And I was also interested into superrigidity, just to try to understand this beautiful work of Margulis. And so in superrigidity, you have this idea that you replace the study of the discrete group by the study of one-dimensional dynamics, which is actually the action of the biofield in that context. So this idea of trying to study discrete groups by studying geodetic flow was really floating around. And for instance, CNGs pointed to me that it was very important to study both the action of the flow and the action of gamma, and the two are related. So that was the background.
Okay.
And then there was this question which was this paper of Hitchin. So Hitchin produced a whole bunch of, we didn't even know they were discrete, but some subgroups of Lie groups. And I wanted to know what they were. So I came up with this tool, but this tool was really floating around, and it's sort of obvious to everyone in the subject.
Well,
No.
not too obvious back then.
Yeah, but
no, I mean, the way Hitchin discovered these subgroups was from a very different place, right?
Yeah. So he was more on the analytic side, Higgs bundle side, and had a little bit of understanding of that using my background on the holomorphic differentials. So I was in between, and I came up with this idea of Anosov representation. And actually, frankly, I really thought of it as a tool, something to study discrete groups. And then I asked people around, they were discussing maximal representation, or they were discussing IDS geometry, and say, are there Anosov groups? And then the study started this way. Yes.
You thought of the idea, but you didn't know if it applied to any examples?
No, I just knew the example of Hitchin representation, and just knew the example of quasi-function groups.
Right. Okay. So that's often something people cite as one of the initial motivating examples. You were thinking of quasi-Fuchsian limit sets, and this is where your idea for trying to make curves in projective space.
Exactly.
Okay.
Exactly. And also, this result that stability of quasi-function groups, which I did not understand the proof. So I tried to work out a different. The idea of the proof, and the idea of the proof was just another representation.
Ah, really? Okay.
So you had no idea how influential this concept would be, and that today we are having conferences about it.
Yeah, no, this was really a surprise. So it really was meant to be a tool to study discrete groups, and nowadays that's what it is. It's not a theory by itself where you have big conjecture. It's really a tool to study discrete groups, which is one of the major.
Yeah, very successful tool.
Yeah. Maybe more successful than you thought.
That's for sure. That's for sure.
And maybe you can say more. So this idea of flows that you were studying with Flamm. So do any of those sort of rigidity ideas end up appearing because we think of Anosov as a very flexible condition. Is there a connection that you could explain?
No, but the idea of the fact that surface groups were more flexible. So I remember that at that time it's come off as this weird classification of mathematics into liquid mathematics, solid mathematics, and gaseous mathematics. So solid mathematics was like Riemannian geometry, gaseous was like set theory.
Okay.
And liquid mathematics were what he thought was interesting. And I always thought that surface groups were sort of liquid groups. They have lots of structures. They are very flexible, but at the same time, the character variety has some structure, which come from the symplectic geometry, right?
Okay.
Which was again one of the other thing I was interested in, which was these character varieties for compact group and Goldman forms and Atiyah-Bott results and everything.
I see. Okay. So surfaces are kind of the perfect
Yeah, there was
Goldilocks.
this liquid groups.
Interesting. I like that. Could you tell us about, we've had 20 years of Anosov representations now. Where is this subject going? What would you like to see happen in the next 20 years?
So the subject, I see it from far away. It's spread in lots of different directions. So we heard talk about how they appear in variation of hot structures, and there are some people who are way more interested into geometry group theory. And well, my own interests, of course, are different in my tiny own subject. So I'm really still interested just in surface groups.
Okay.
And for instance, I'm still fascinated by the geodesic lamination of that Thurston introduced. And so is there any other situation where we have objects similar to geodesic lamination? Very concrete objects. So that's the power of the thing, that they are very concrete and powerful.
You mean something like the Thurston compactification, where we see...
That's one way.
Yeah.
So there are lots of compactification these days, but and there is this spectral network coming from physics. And so it would be nice to sort of unify all that and try to find what is the correct object here. So that means this idea of higher geodesic lamination and the idea of what would be the intersections. And there are lots of candidates, but we don't have yet a theory which I grasp enough myself. But maybe it's a limitation.
So you think there's some sort of deep structure hidden in a surface that no one has found yet, that's when we find it, it will be like when Thurston described laminations?
I don't know. Actually, I don't know. I would love that to know, but maybe they don't exist, right? Who knows? That's, yeah.
I think we should keep looking, right?
Yeah. So maybe a question, I mean, you seem so fascinated about mathematics. Like, I don't know, can you tell us a bit about how was your path? Like, how did you get interested in mathematics? And
that's a very good question, but as I told you, that's a very embarrassing one because I was not interested in mathematics as a kid. And so you have to understand that, so maybe you can guess from my accent that I'm French. And in the French education, there are tubes. And if you're a good student in whatever subject, you end up in the beginning of the tube, and you end up doing mathematics at the end of the tube.
Okay.
So I didn't really choose. I didn't like that much mathematics when I was a kid, when even I was in a high school or I was in college. But then I went to École Normale and I discovered it was pretty cool.
But how did you discover it? Like, you liked everything?
No, I liked. So we had two professors. I'm not going to give names. So one gave amazing talks, perfect. But then when you exited the talk, you just can't remember anything. And the other one was totally chaotic.
Okay.
And I really like the chaotic ones. I try to understand what he says, and so I like I like that. So that's due to this professor. And then.
So you prefer a chaotic lecture style then?
Well, maybe not anymore, and not when I give them.
That's cool. Okay, so once you got to École Normale, you sort of became ignited and
yeah.
Sort of
So
went
that's
there.
when I started liking mathematics.
And how did you get interested in like your research you're doing today? Like
okay. So
dynamics,
that's actually a very interesting point,
geometry.
because I was very focused on the subject of my PhD. I was working alone, and then I was in this office, and there was this guy, Patrick Foulon, was sharing my office, and he was nagging me always with questions.
Wow.
It was very annoying.
He was another PhD student at the time? Or?
No, he was it was 2-3 years after my PhD.
Okay.
So it was at École Polytechnique at the time.
Okay.
So he was keeping asking questions. So I think the fact of being as a young person in the office of someone who does something totally different is very helpful. So
Yeah.
I came up to this. So if there is one advice to young searchers is to be in an office with someone who does totally different mathematics,
Okay.
and that would maybe help and give you some new ideas. I don't know.
Interesting. Okay. Do you share an office?
Yes, I do. With someone who comes from biology,
Okay.
mathematical
Hey,
biology.
there you
so
go. Okay.
yes, and before it was not theory. So
Okay.
Okay.
yeah.
Maybe we can turn to the topic of some of the actions you've taken towards helping young researchers. So, I'll say again, your research has inspired many and a lot of mathematicians, a lot of activity, but you've also dedicated a lot of energy and resources towards training the next generation of geometers. For example, you dedicated the Louis D. Prize and also ERC grant resources to funding research activities for young mathematicians. Can you tell us about your motivation and your vision for these types of endeavors? And more generally, what do you think the larger mathematical community could be doing differently in the area of training and inspiring the next generation?
Okay, so I think there is lots of different models, but the one model I try to and they are all good, but just the one I'm comfortable with is that when I organize these schools for PhD, postdocs, and maybe even master students, I try to cover a very wide selection of topics.
Okay.
That means that, for instance, this school that I will organize in Nice, there is something who is going to talk about quantum representation, someone who is going to talk about currents and classical Teichmüller theory, someone who is going to talk about probability. So I think it's very important that to try to make the young generation aware that there exists other mathematics than the one they have to do right now to get a job. Of course, I was lucky because I got a permanent job at 27. And I know it's much harder for young people these days.
Yes.
But it's still important not to stay too focused. And it's really important to learn new mathematics, even way far from your subject. So that's what I try to do in these schools I organized.
Okay.
And then the other model was the one that was created by the GEA network, which was this log cabin person where young people gather together and find a subject and discuss it. So here's the point: is just to give money. So that was the point of Louis D. Prize.
Yeah, I took some of that money. I went to these workshops. It was really great.
But then I had no scientific influence on that. It's just, okay, here's the money, organize something, discuss together.
I see. Okay. But you insisted that it be kind of broad. That's
not for this log cabins kind of stuff.
Okay.
But for the school organized, I always wanted it to be broad.
Yeah.
But again, it's very nice to have something focused as well. So
I think I was at the first gear log cabin workshop myself a long time ago, and that was how I first learned about Anosov representations when I was a student.
Yeah. Actually, me too. Like mine is also one of these workshops.
I mean, it can be a challenging subject to penetrate. So somehow getting a bunch of people in a room somewhere secluded
or getting someone to explain it to you.
Yeah.
Is there any other advice that you could give to young researchers?
Okay, so, well, it's not really an advice, but the community is facing a problem. There are way too many papers being written. So, of course, it's important to, when you apply to a job, to have as much as paper being written as possible.
Yes.
And but I think it's important that people not try to write too incremental papers where they study this case, but then the case a little more general, then a little more general. So it would be, but then for that you need to stop and start thinking and not worrying about what your next job is going to be, right?
Yeah. Yeah.
I don't know. I don't know how to solve that, but we all have noticed there is way too many papers. That's a lot of job for. That's a lot of work for everyone. And then you are confused about who has written what and what the overlap of this paper on this paper. So
I see.
That's a problem, which is related to the job situation for young people, and I don't know how to solve that.
I see. But do you think, waiting a little bit longer and trying to improve your results to write a better paper could be a good move for someone who's in that limbo of searching for the next job? Or
this seems tough. I don't
yeah.
know.
Like in research, you never know.
You never know if
Right?
you're going to converge or not, if you're going to solve that nagging next problem, right?
Yeah. And it sounds like for you, I mean, this idea of breadth has been really important, of not getting too hyper focused on one thing, but allowing yourself to sort of float towards other topics and see how your ideas can connect with other types of ideas, and it's led to some great things. So maybe we can all take some inspiration from that.
But I think that's because we all love surfaces, and surfaces are, there is this analysis, Laplacian, and then there is discrete geometry, and then there's the dynamics. So
it connects to very
different mathematics, number theory, and
many fields. That's also what makes it so interesting.
Yeah.
So you already talked about this, like a challenge for our community, and then I wanted to ask you about something else. Like on your website, I saw that you signed a petition to limit the use of planes, and I was wondering, like, how we as a mathematical community, like all together, can like face this challenge, because we are very international. How can we take collective action? Do you have some concrete suggestions, and what influences could this have on our work, or how we do mathematics, or how we work together?
I think that's a discussion that we should have as a community. So first, maybe I should say that this is the only petition I've signed. So
Like ever. Okay.
Maybe a second one. But and so we face this problem as a community, that we are very carbon costly. And I've been in many countries. I'm not so proud of that these days. And so we have this question: how do we find a way, first, to keep meeting people, because meeting people is so important. And so I guess that the problem is a little bit different for young people and older people. So actually, I think the text of the petition makes a difference between senior researchers and junior researchers. So junior researchers should travel more. So there is the travel thing, but then also I'm organizing conferences. So how do I find a way to minimize the carbon footprint of this conference? For instance, during COVID, we learned how to use Zoom. And this is very productive. But we also gave Zoom talks on conferences. Now we hate that. But,
we do.
But maybe there is a way to still give some conferences use some sort of balance between all the whole world circles coming in one place, and then people giving Zoom talks. So we have to find some balance, and we have to find something. But it is really a problem that we should think about it. And maybe there is some technical solution, maybe there is not. But anyway, what I do is try to limit myself and just travel once a year by plane, which I have not succeeded so far, I'm afraid to say.
Well, seems like a worthy goal. I mean, do you imagine like a hybrid model for conferences? There's been some success in that.
I think some people have organized a hybrid model. So, for instance, conferences in several nodes, let's say one node in Europe, where everybody can travel by train.
So people are together, but watching some talks on.
And then there will be some other nodes at some other one. But I don't know how successful this was.
Okay. Interesting.
I mean, we are also very privileged here in Europe that there's so much mathematics, and that we can easily access
You know,
Yeah.
without
Like-
planes, I would be alone.
That's true.
Yeah,
In
I
Texas, you
I have
lost
plenty of people to
forever.
talk to in Texas, but not in this particular
Yeah.
subject.
Yeah, but even in Asia,
Yeah,
it's even more
Yeah.
secluded, and these people still need to meet the
yeah.
the
We need
mathematical
to stay
community.
connected
Yeah.
as an international community.
But I guess some people are thinking more about that than I do, right? So maybe it would be more interesting to discuss with these people, right?
Okay.
than with me.
Okay, so maybe one final question. Do you have a mathematical hero
Or heroes.
Or
or heroes?
So I'm not that young, so I've met a lot of person in the community. There's not so many mathematicians, so I've been lucky to meet a lot of extraordinary mathematicians. I'm not giving names, but lots of really extraordinary mathematicians. But because of the mathematics they do, but I like also the way they behave in conferences and the way they ask questions. And there's two persons I would like to, was very impressed by. So one was when I was a young person, Sullivan was very often in France, and he has this totally naive way of being in conference and then asking questions when he doesn't understand.
Okay.
And it's still true that people are afraid of asking questions during conferences, looking stupid, right?
Yeah.
He just didn't care. He never looked stupid, by the way.
But he was Sullivan.
He was something, right? So, but this way of asking questions, and even if he discussed with you, he would ask questions, be interesting. That was something very I liked a lot. And the other person is Marianne Mizrahi, which I was lucky to know personally. And when she was doing mathematics, so she was, of course, an exceptional mathematician, but when she was doing mathematics, she has this amazing way of thinking about the problem and then coming with this question. And then you said, oh, that's the question I should have asked myself. That's really the question that's going to solve the problem. So this is something I was very impressed with, the fact that, I mean, in mathematics, important thing is how do you ask questions? Question that everybody can understand also. And okay.
Yeah. Okay.
Great.
Thank you so much, François. And thank you to the MPI again
Yes.
for having us.
Yes, thank you.